All right, guys, let's start talking about RTDs. An RTD stands for Resistance Temperature Detector. So the symbol for an RTD is right here. So you can see that that the actual resistor is here, and then they have a line through it to show that it's a variable resistor. So essentially what an RTD is it's a variable resistor, and the resistance changes with temperature. As usual, as I go through my PowerPoint here, there'll be links here. So if you wanted to follow along with me, each of these different photos or diagrams that I've grabbed from the internet, the link is below. They're live links, meaning that if you go to in the comment section, there will be a link there to my website. You can download the PDF. You can follow along with me. And then later on, if you want to learn more on each of the different topics that I'm talking about, you can go to these links to see where I've gotten the picture, and they'll provide you with more information than what I've provided here in the video. All right, so moving on. RTD, resistance temperature detectors. So what is an RTD? Well, like I said, it's a temperature sensor that exhibits predictable increases in the resistance as the ambient temperature increases and decreases. So it's essential that we want to have something that is repeatable and really precise in order to provide us with a temperature value. So this guy does it by providing us with a variable resistance, but that resistance is really, really tight. Like, it's very accurate and it's very repeatable. Anytime you pick up a PT100, it's always going to have the same characteristics as another PT100 that you get from another manufacturer. Tolerances are tight. Accuracy is really tight. They're a phenomenal way to take a temperature reading. Okay, we'll get into what each of these guys are and the different housings as we go through, and then we'll get into the wiring as well. So what I might do is, as we go through, if you don't want to hear the first preamble, you just want to know, all right, I have a 3-wire PT100. How the heck do I hook it up? I'll give you the link to the value or the time frame, and you just click on that. You can go to it. So go to the comment section. You can fast forward through. Okay, so RTDs are similar to thermistors in that their resistance varies in direct proportion to the changes in the ambient temperature, right? We looked at the thermistors in a previous video. We found that they had a negative temperature coefficient. We found that the graph basically went like this, right? So that as the temperature increased, the resistance decreased. Okay, RTDs are the same as a piece of wire. It's a piece of platinum wire. And as you heat up that piece of platinum wire, then the electrons start to move faster, and it's harder for them to transfer all the way through the metal. So as the heat goes up, the temperature goes up, and the resistance goes up as well. So RTDs are always going to exhibit a PTC, or a positive temperature coefficient. What is an RTD made from? So most of the time I say the previous slide earlier on, but RTDs are made from platinum. There are other RTDs made from nickel and copper. They're cheaper, but they're not as reliable as platinum. So pretty much any RTD that you pick up right now is going to be made of platinum wire. If we look at each of the different metals that we mentioned, nickel and copper, nickel has a limited temperature range because the amount of change in resistance per degree change in temperature becomes non-linear at temperatures above 300 degrees Celsius or around 570 degrees Fahrenheit. So we want to have a piece of metal that provides us with a linear output. Like, look how gorgeous that platinum line is, right? Whereas if you look at the copper or the nickel, at a certain temperature, all of a sudden you get into non-linear outputs. And when you get into non-linear outputs, it's very hard to standardize that output and then have it come out as an accurate value. Whereas if you have a linear value, then you can just correlate a value in resistance to a value in temperature. Okay, we saw that with the thermistor. It was kind of a pain in that it had that negative temperature coefficient and it had that exponential curve, and we had to use a specific equation in order to take that exponential curve and then correlate that to temperature. With these guys, it's basically a linear output, providing us with that direct correlation with the temperature. So nickel's all right, but it's not great. Copper, we know, is going to oxidize, right? They say it can't be used over 150 degrees Celsius. Not sure why it can't be. I never found that out. Just copied and pasted and didn't have the time to look further into it. It has a very linear resistance temperature relationship, but it has a low resistivity. So another reason why they don't use copper that much is that because it has a low resistivity, it requires a long length of conductor to actually produce an acceptable sensor. Right? If you want to look at the resistivity values, they are right here on each of the slides. Okay, you can see here that platinum has a large change in resistance for each change in temperature. So platinum is the way to go. Right? So platinum has a linear increase of 0.385 ohms per degree over a wide temperature range. That's specific to the industrial PT100. We'll look at different ones in a little bit, but that's essentially your standard there at 0.385 ohms per degree. It has basically the best accuracy and the best stability out of each of the metals that we've talked about. The very high resistivity, so only a small amount of conductor is required to create a sensor. Well, that's great because platinum is disgustingly expensive. And you can see the value here of 59 compared to copper and nickel below. Okay, what temperature range? So basically the difference between whether you're going to use an RTD and whether you're going to use a thermocouple is what temperature are you looking at. Or if you're looking at a disgustingly high temperature or you're going to put something right into a flame, you're most likely going to use a thermocouple. If you're not, then you're going to use a thermistor or an RTD. RTDs are basically giving us a linear output between negative 200 degrees Celsius and 500 degrees Celsius, or negative 328 to 932 degrees Fahrenheit. And again, on this graph, you can see in degrees Celsius, the linearity of the platinum versus the nickel and the copper. So are there different types of RTDs? For sure. And there's probably going to be new ones coming out, in the next 10, 20 years. So we have the thin film RTD, which is this bad boy right here. We have the wire wound element RTD. The element is basically the piece of wire. And then the next one is the coiled element. So I'll go through each of them individually. Let's start off with the thin film. So the thin film is like a really small housing, great for like fine measurements and in a small putting something into a small housing because it basically consists of a layer of platinum on a ceramic substrate, and the actual platinum is disgustingly thin. It could be as much as just a micron thin. The RTDs are very fast to respond to temperature changes. That's because they're basically sitting on a large heat sink and you have a very thin conductor. And so that resistance is going to change drastically with each temperature change. Okay. But again, these are not large. These are like, I don't know, the size of your nail on your pinky or something. Right? They're not very large at all. And sometimes you'll find that they're also housed in the same housing as the other elements that we're going to see next. So you can't really discern which type it is just by looking at the protective casing around it. The next one is the wire wound sensing element. So with this one, you're going to take a small diameter platinum sensing wire, and you're going to wrap it around a non-conducting cylindrical ceramic rod, or what they call a mandrel. And then in order for that to withstand high temperatures, you're then going to coat it in either ceramic or a glass coating. Okay, so essentially what you have, if you follow this through, is a piece of wire that is then wound around a mandrel, goes back out, and provides you with the other lead, right? So in order to increase the surface area, they're just winding across this mandrel right here, and collectively they're going to change resistance as the temperature changes. Okay, the last one is the coil sensing element. This one is the one that's kind of becoming the most prevalent in industry. That's because it has a strain-free design. Remember that if you have a piece of wire, as it heats up and as it cools, it's going to expand and contract. Well, if you have it, in a tight housing, then as it expands and contracts, wherever you've grabbed it in order to keep it in the same position, that's going to cause a strain on the conductor. And that strain itself is going to change the resistance of the platinum. So we want to have a long coil of wire so we can get the most surface area and the smallest housing. But we want it to be basically free floating. We want it to be able to expand and contract without being constricted and having that constriction changing the accuracy of the actual element. Okay, so the sensing element is a small coil of platinum wire that resembles like a filament on an incandescent light bulb. The coil is then inserted into the bores of the mandrel. So you can see that it's going through the bore, back out to the other side, to the other lead there. And then the bores are then packed with a finely ground ceramic powder. So the ceramic powder provides it with the insulation electrically and thermally, but also because it's just a powder, it's able to move without being constricted. Okay. The equation for the resistance temperature formula for an RTD is right here. So we have the resistance is equal to the resistance at 0 degrees Celsius, because we have to have a reference point, right? And then the other thing that comes into play is the alpha, which we also call the temperature coefficient of resistance. And then delta T would be your temperature change. So RTD sensors are usually manufactured with a resistance of 100 ohms at 0 degrees Celsius or 32 degrees Fahrenheit, and an alpha value, or that temperature coefficient, of 0.0385. Remember, we said it, that was the change in ohmic value per degree Celsius. Okay, there are different types of RTDs out there. This is your standard, the 0.0385. That's the IEC standard. But there is a value of 0.03916. So there are the same RTDs. They look exactly the same, but this one has a different temperature coefficient. You'll find these in laboratories. You'll find these in industry. Okay. And again, you can see here, the benefits of each of them with platinum, copper, and nickel as you go through. Platinum is basically the best one that we can use. Okay, so pure platinum has an alpha of, so I've grabbed this from Wikipedia. The link is right here. This is a good link to go to for generalized stuff on the RTD if you want to follow up on more information later. But again, the platinum has an alpha of 0.0392 ohms per ohms per Celsius in the 0 to 100 degrees range. And that's for the laboratory grade RTDs. The industrial RTDs, those have an alpha of 0.00385 ohms, right? Now, these two values right here, right, those different alpha values for platinum are achieved by doping, basically carefully introducing impurities into the platinum. The impurities introduced during doping become embedded into the lattice structure of the platinum and result in different resistance versus temperature curves, and hence their alpha value. That's why you stay in school, and that's how you get your PhD, so they become an expert in creating RTDs for industry so we can get these mid-temperature values off of our temperature sensors. Where does that name PT100? I mentioned that earlier. Well, PT stands for obviously platinum, right? We said that the reference point there was that a PT100 RTD has a resistance of 100 ohms at 0 degrees Celsius. So the PT100 is just telling you everything about that RTD. It's a platinum piece of wire that has a resistance of 100 ohms at 0 degrees Celsius. Okay. We said that it has that alpha coefficient, right? Meaning that it provides us with a linear increase per degree of 0.385 ohms per degree. So you'll find that there's a chart. So if you type into Google or any of your search engines, PT100 resistance to temperature chart, it'll come up with this table right here. And we can see here that the change, so they've rounded it by 1 decimal place here. But again, it goes up by 0.385 ohms per degree. So again, at 0 degrees Celsius, we have 100 ohms. And then as we go up by each degree, so 1 degree is going to give you 100.385 or 100.39, right? Then we go up to 2 degrees, then we're at 100.78, and it linearly increases all the way through on this lookup table. So essentially what we can do is we can take the resistance of the RTD, which corresponds to the voltage that we're going to get off of it. So if we keep the same current across the resistance or the RTD, then the voltage is going to be directly proportional to the resistance. We're going to look at the voltage, we're going to extrapolate the resistance, and then this chart right here tells us that at that resistance right here, it tells us exactly what the temperature is going to be. Okay, does the RTD provide a linear output? So this is like when I finish off and we go through all the test questions, everything, this would be a mint test question. Does the RTD provide a linear output? Oh yes, it does, right? Gives you that nice linear output here. This is also from a great link here from instrumentationtoolbox.com. Great resource for a number of different things, primarily right here for RTDs, but take a look at their link. They've got a great website to look at. So RTDs exhibit relatively linear resistance to temperature curves over their rated temperature values. Obviously, it's going to go non-linear above or below certain values, but in this range right here, it's mint. Nice linear output. Okay, as we go through, that chart there is quite large, right? So I've took a screenshot here from Omega. This is from one of the suppliers here, and you can see that the chart for the 0.0035 PT100 is quite large, right? We're going from, if we go back here from minus 200 degrees Celsius to 850 degrees Celsius. So the RTD has a nice, massive range of temperature. But again, if you're going to get up above 850, your RTD is going to just smoke, right? So you're going to go with a thermocouple, most likely. Okay, conditioning of the RTD output. So they're a passive component, right? So they need to have current flow through it in order to create a voltage. All it is just a resistor. You're putting a resistor into a specific circuit and you're going to get a voltage output. But on their own, they're just a passive component. They're not like a thermocouple that creates a millivolt output as the temperature changes. As the temperature changes on this guy, all it does is increase or decrease its resistance. So typically what we're going to do is we're going to put this guy into a voltage divider, or we're going to put it into a Wheatstone bridge circuit. If you haven't done any research on Wheatstone bridges, they're used quite a bit in instrumentation. They're just a really cool way to look at series and parallel circuits. Essentially what you're doing is we had all four of these guys being equal resistance values, and then we took a voltage reading here, as long as we have our source voltage applied to it, then if all four of these bad boys are the same, then the difference between this point in the circuit and this point in the circuit should be 0. If we put in an RTD or a variable resistor, as this resistance changes, then the ratio of these two voltages is going to change. And then the ratio of this point to this point, the potential difference between those will change as well. And this voltage will linearly change in correlation to the resistance change on this leg of the Wheatstone bridge. It's a really cool circuit. If you haven't looked at it yet, Google Wheatstone bridge and go down that rabbit hole. Okay, so when you go and buy an RTD, there are 3 different types of RTDs you can purchase: a 2, a 3, or a 4 wire. Most likely, if you're going to purchase an RTD and you're using that in industry, you're going to be using a 3-wire RTD. Right? Just to read everything I have on the page here, one of the greatest accuracy challenges of dealing with the relatively low resistance of the RTD. This is because any lead resistance of the RTD assembly can add significant error to the measured resistance. So as you increase the number of leads on the RTD, you're going to get a more and more accurate value off of that variable resistor. Okay, and we'll see that in the coming slides here. 2, 3, and 4-wire lead compensation techniques are used to provide increasingly accurate readings from the RTD assembly. So let's start off with the 2-wire RTD. 2-wire RTD is just, I need a temperature value, but I really don't care about the accuracy of that value. I'm not going to have it as a long run. I'm just doing a short run. Maybe I'm using it for HVAC. I really don't care if I'm plus or minus, 2 degrees. I just need something to turn on at a relative temperature value and turn off at another one. So maybe in HVAC, you'd see a 2-wire RTD, right? It obviously has the lowest cost, right? Less conductors then means less cost. Used only when the lead wires are short, rarely used due to high error from lead wire resistance. And I said that, the one application that I found was that you'd find them in HVAC units. So the problem with this guy is that you only have 2 leads. Again, the standard for these guys is that the conductors for an RTD are red and white. So this would be the other end of the RTD assembly. When you hook this guy up, you have the resistance of this wire and the resistance of this wire being here and here. It's a series circuit. So as you're trying to take a voltage value from this guy, well, these 2 resistance values on your leads are going to skew that value. You're going to have a higher value than what you were looking for. And obviously by changing that value by 2 or 3 degrees, that can really skew the resistance value, right? And your temperature value that you're getting off of it. So cheap sensor, works great, but not all that accurate. Okay, again, if we take a look here, that this lead resistance is adding to the RTD as well as this lead resistance. And there's no way of eliminating that lead wire resistance from your sensor measurements. So essentially the temperature reading that you're going to have is going to be artificially high from a 2-wire sensor. Okay, if we take a look here, if the lead wire resistance is 0.5 ohms, then the instrument would read 2.6 degrees higher or 4.7 degrees Fahrenheit higher than it should. That would mean that we have, because of series circuit, we have 0.5 plus another 0.5, giving us an extra ohm of resistance. The PT100 has 0.385 ohms per degree Celsius. So if we take that 1 ohm of resistance that we've added to the RTD, divide it by our alpha here, then you're going to find that the actual temperature reading is going to be off by 2.6 degrees Celsius. If you're using some code, maybe you can take your code and get rid of that, but it's better to just purchase a 3-wire and have an accurate value. Okay, again, you may be using an Arduino, you may be using a Wheatstone bridge, but you can see that from this point to this point right here, as we go through this circuit, well, we have this resistance plus the lead wire resistance. So we have 2 resistors on this leg. Then we go through the RTD, but coming back to the other side, we only have 1 resistance here for the lead wire. So you can see that 2 resistors and 1 resistor are going to skew the value of the RTD. So we need another resistor in there to balance that value out. So we're going to be making use of a 3-wire RTD. Okay, so using a 3-wire, we're going to get a more accurate signal from the RTD. The 3-wire color codes are that instead of having just a red conductor and a white conductor, the 3-wire RTD is going to have 2 reds and a white. The 2 red conductors here correspond to these bad boys right here. So we have an additional conductor coming off of the one side of the RTD. This provides us with the best balance of cost and performance, meaning that we've got another conductor that's platinum. Obviously, the cost is going to go up, but compared to the 2-wire, this has really, really good accuracy compared to that RTD with just the 2 wires. So the 3-wire is going to be your most common type of RTD that you're going to see in industry. Unless you're working in a laboratory. In a laboratory setting, you're probably going to be making use of a 4-wire. 4-wire provides even more accuracy than this 3-wire. But anytime you're going to be purchasing an RTD, purchase a 3-wire and the transmitter to go with it, and you'll have the best accuracy for the best price. Okay, so it's providing us with the best lead wire compensation. You can see that on this diagram right here from instrumentationtools.com. If we take a look at the lead wire resistance, well, if we take the first resistance for R1 and the second resistance and our RTD and we add all those guys up together, if we subtract this resistance right here from R2 through to R3, then essentially we would be eliminating the lead resistance and just be left with the RTD value. Okay, so by putting in that additional conductor there, we can eliminate the lead resistance, providing us just with our RTD resistance that changes with the temperature. Okay, so if we take a look at the Wheatstone bridge, then we can see that this guy would be our white conductor. These 2 would be our 2 red conductors. Another way to look at this is that you've provided the RTD with power. So we have one conductor here providing one side of the source, this conductor here providing with the other side of the source. And this conductor here, this lead conductor that goes to our voltmeter, well, our voltmeter is going to be a high impedance path, meaning that very minimal current is actually going to flow on this lead resistance. So at that point, then we've again eliminated the lead resistance, and whatever voltage comes in here won't be skewed by this resistance of the lead conductor. Essentially, there will be a voltage there, but very minimal current actually flowing because of the high impedance path of the voltmeter. So by using a 3-wire, you give yourself really high accuracy values from the RTD. If we take a look again at that circuit, right, just in a different form. So this is here from globalspec.com, and they provide us with a better, or not a better, but a different way of looking at it. So here we have our lead resistance, right? So following this current flow here, we have lead resistance. Then we've got the RTD and another lead resistance. So you can see that with just a 2-wire, these two lead resistances are going to add to the RTD, and then it's going to skew the resistance value, which is going to give us a higher temperature value than what the RTD is actually reading. If we take another meter reading here, though, from this point right here, and we see the voltage dropped across this lead resistance and the third lead resistance, then the voltage that's available here is essentially just the voltage, the voltage that's dropped across 1, 2 lead resistances. So if we take this value right here and subtract it from this voltage right here, then essentially what we've done is we've removed the 2 lead resistance values, and all we're left is the voltage change across the RTD. And that voltage change across the RTD will be directly proportional to the resistance change, and the resistance change is directly proportional to the temperature change. So now we've got a value that is specifically just the RTD value and no longer has any of the lead resistance as a part of that equation. Okay, if we take a look at the 3-wire that I'm going to use for the Arduino project that's coming up. So just after this video, I'll be doing using an Arduino and using an amplifier from Adafruit. But aside from the amplifier, let's take a look at the specs on this 3-wire RTD. So this guy says that it has, again, it's a PT100. So it has usable temperature range between minus 200 to 550 degrees Celsius, or minus 328 to 1022 degrees Fahrenheit. So we covered this earlier, right? In the normal temperature range for an RTD. Obviously uses the 3-wire interface. Has a plus or minus 0.5 degrees Celsius accuracy from minus 10 to 85 degrees Celsius. So we'll have to keep that in mind. Regardless of how accurate we try and make our code, we could be plus or minus 0.5 degrees Celsius all told when we're finished. So we're not going to get exactly the temperature that is in the room. We may be 0.5 degrees Celsius off. The resistor material is platinum, obviously, because it's a PT100. And again, that 100 is coming from the 100 ohms at a temperature of 0 degrees Celsius. So we covered that as well. Platinum has a positive resistance temperature factor. So remember, it has a PTC. So as the temperature rises, then the resistance is going to increase. The resistance variation is a function of the temperature with a 0.385 ohms per degree Celsius nominal. So remember, that is the alpha or the temperature coefficient for the PT100. Remember, that's a standard across all the different manufacturers. And it's saying that the PT100 is providing us with high accuracy and stability compared to thermocouples, silicon-based temperature sensors, or thermistors. So hopefully we've covered each of these different points so we understand exactly what we're reading off of the cut sheet now. There is also a 4-wire RTD, but again, the 4-wire RTD is most likely going to be used in a lab setting. It has obviously the highest cost because there's more platinum there, but it's going to give us the best lead wire compensation. Again, if we take a look at the diagrams, either from this link right here, flowcontrolnetwork.com, or from instrumentationtools.com, you can see that the 4 wires are connected here. We have a lead here going across the RTD, another lead going back to the source, and then the voltage that's coming across or being read across the RTD would be measured across these 2 resistors here. So we have 4 leads there. The reason why it provides us with the best value in voltage corresponding to the resistance of the RTD is again that we're providing this guy with a constant current supply. So we have a constant current supply, and so the change in resistance is going to be reflected with the change in voltage. So as the resistance changes, so as the temperature goes up, the resistance is going to go up, and we're going to get more and more voltage available between these 2 points. The thing that's actually reading the voltage is a high impedance voltmeter, meaning that all the current is going to be flowing in this direction here, from one side of the source to the other. There will be a voltage that develops here, but there's very minimal current that will flow on this lead resistor and this lead resistor. So we've got a voltage here, but it's coming off of a very low current flow, right? There's very minimal current flowing here and very minimal current flowing here. So whatever voltage we see here is pretty much exactly the voltage that's going to be across the RTD. Because of the fact that this is a high impedance load, very minimal current flowing through these guys. So these resistances of the lead wires are basically going to be non-existent. This voltage is now going to be exactly the same as this voltage right here. So with the 4-wire, it provides you with the best accuracy available. And again, one more time, that's because the current is flowing through the RTD here. There's minimal current flowing here. Minimal current means that there's minimal voltage drop across those 2 lead resistors. And whatever voltage we're reading here is essentially the exact same voltage as you'd see right here across the RTD. So now we've got a great way, the best accuracy available in order to get that voltage across the RTD transferring right into our microcontroller. Okay, another way to look at that is from this diagram right here. And if you go to this link right here, so when I'm finished, go to the link below, and this guy right here will go through the 4-wire and hopefully explain it in a different fashion. So if I haven't made sense on why this provides the best voltage value using 4 leads, then go check out this link right here, and hopefully it provides you with a little bit better background. Okay, number of different resources. So each of these resources are available on each of the different slides if you want more information when you're finished watching this video. Okay, in addition to the RTD, right now what we're going to do in the next video is we're going to use the RTD and we're going to use the Adafruit amplifier. And it's essentially going to take that changing resistance on the RTD and then be able to compensate for the lead resistance and provide us with a voltage into our Arduino. If you're out in the field though, you're not going to be using an Arduino, you're going to be using a standardized transmitter. So what happens is that if you were to transmit that small voltage from the RTD across your conductors all the way back to the control room, then you're going to have voltage drops and everything's going to be skewed. So right there at the RTD, you're going to have a standardized transmitter. That standardized transmitter is going to take the changing resistance on the RTD and change it into a standardized signal. If it's going to go quite a distance, then it's going to be standardized to a 4 to 20 milliamp signal. That value can go like 1,000 feet. It's a series circuit. And so the change in resistance on the RTD will then be changed into a voltage. That voltage will be changed into a standardized signal of 4 to 20. And that 4 to 20 milliamp signal will now correspond to your temperature range that you're looking at. If you're using a digital field bus output, then instead of using the standard 4 to 20, you'll be using a digital signal using HART or Foundation Field Bus or Profibus. And those essentially will be providing a digital signal that provide both the temperature value and the address as to where that temperature transmitter is actually mounted out in the field. And each of those guys are going to be on the same twisted pair instrumentation cables that we've been using for all of our transmitters. Okay, advantages of RTDs. So hopefully we've gone over all these already, but let's just quickly run through them. The advantage of the RTDs is that the temperature range and linearity are superior to both thermocouples and thermistors. They're more accurate than thermocouples within a certain temperature range. You don't have to do the additional compensation for cold junction compensation that you would for thermocouples. The nice thing is that compared to the thermistor, they have a linear output over a wide operating range. They have a high accuracy, usually of 0.1 degrees Celsius, and low drift. The operating temperature range is quite large. It's between minus 200 degrees Celsius all the way up to 850 degrees Celsius. The platinum provides us with a good long-term stable output, and it's commonly used in applications where accuracy and repeatability are important. Okay, if we take a look at the response time, so one of the drawbacks of the RTD is that there's a larger response time because it usually has to go through the thermowell and then go across the RTD. All right, so if we take a look here, this is from foodengineeringmag.com. For those who would like to use RTDs but haven't used RTD response times because they're inherently slow, this is one of the manufacturers. Anderson Hauser has come up with a thin film RTD that we talked about before that has a response time of that of a thermocouple. Traditional RTDs in a 9mm thermowell have a T90 response time, the time needed for 90% of the process step change to be reflected in the output signal, of approximately 20 to 45 seconds depending on the technology, which is that wire wound or thin film. Anderson Hauser's quick sense RTDs can reduce the T90 performance of a probe in a 9mm thermowell to approximately 5 to 20 seconds depending on the geometry. So that's that thin film RTD that we saw. It's mounted inside of a thermowell, and this is one of the main drawbacks of using a textbook. Usually by the time a textbook comes out, they'd be saying that the RTD has a slow response. Well, now it doesn't have a slow response. It's basically in line with the thermocouple. So the drawback of using, a standard textbook in class is that by the time it's published, the manufacturers have already gone beyond that. So now we can see that the RTD has a really good response time, very close to the thermocouples that are out there. Okay, disadvantages of the RTD. They have a small overall temperature range compared to the thermocouple. They have lower sensitivity than the thermistor. They're bulky in size. That slow response time, see that there is no longer true because in different housings with the thin film technology, you can get a really good response time now. Higher cost than thermocouples. Susceptibility to self-heating and lead resistance errors. So that is one of the major drawbacks of the RTD is that the lead resistors or the leads are going to provide resistance, and we've already gone through the errors that are going to happen because of that. The other problem is that you have current flowing through that RTD. That current flowing through the RTD is going to create self-heating, and that self-heating is going to skew the temperature value that you're trying to get. Requires 3 or 4 wire operation for a decent value. And the other drawback of the RTDs is that it is a thin piece of platinum that's wound around that's similar to the filament on a light bulb. And so if you're in a high vibration environment, meaning that there's a lot of vibration happening, the RTD is moving quite a bit, then that vibration could cause that thin filament of platinum to break. So over time, that in a high vibration environment, the RTD is going to fail. Okay, if you wanted to stop the video right here, this will give you all the advantages and disadvantages of the thermocouple, the RTD, and the thermistor. If you're looking for the link for here, there's a link here to National Instruments, and they've got their chart that you can go through. Okay, again, they have another white paper here where they've gone through all the advantages and disadvantages of the thermocouple, the RTD, and the thermistor. So when it comes to test time, jot down this link right here, because this is going to give us the best. These two links right here are going to give us the best understanding of each of the thermocouple, RTD, and thermistor, and the advantages and disadvantages of each. All right, guys, let's quickly run through the applications of the RTDs. So there's just a few photos out there on Google on actual uses of the RTD and photos of them out in the field. So if you guys do have photos of an RTD being used out in the field, then forward them to me. My email is vri.peter2@gmail.com. And then I'll bring it into this PowerPoint here. And then any teacher that's using this PowerPoint from here on in, including myself, will be able to provide you guys with decent photos of the RTDs being used out in the field. But you can see they're used everywhere. air conditioning and refrigeration, food processing, stoves and grills, textiles, plastics, petrochemicals, microelectronics, air, gas, and liquid temperature measurements, whether it be in a duct or in a pipe, or in exhaust gas temperature measurements as well. So let's finish off by going through some photos from Google that I've been able to find of RTDs out in the field. So we'll start with this guy right here. So here we have the temperature transmitter that's mounted on the top, and then it has a flange, and then below here would be this portion right here. This is called your thermowell. So the thermowell is the protective housing that goes around the RTD, protecting it from the gas or liquid that's going by. So as the gas or liquid goes by, it wicks its temperature onto the thermowell. That temperature then gets transferred to the RTD. The RTD's resistance changes. That provides us with a change in voltage. That voltage is then seen by the transmitter and is then sent out on these conductors here as either a 4 to 20 milliamp current or as a digital signal. The digital signal being Profibus or Fieldbus or HART. Right, so you have either the 4 to 20 as just a standard analog signal, or you have a digital signal that provides the temperature value and where this transmitter is actually mounted. So it'll provide an address for it as well. It'll also provide another signal to say whether the temperature is starting to drift past the manufacturer's specs. So it'll tell you whether it's going out of whack way before it screws up your control system. Again, here we have two different diagrams here of piping systems here with the RTD mounted and the temperature transmitter mounted above. Here we've got two mounted. So for redundancy, they've got the two RTDs mounted in the same piece of pipe. Okay, this one here is from Anderson Hauser, right? This one has the ability to have the quick connect for the wiring here, so that if the transmitter goes out of whack for some reason, or the wiring gets smoked by somebody going by with a tow motor, you can replace either one and be quick to bring yourself back online. Okay, here it's hard to make out, but there are three different RTDs, 1, 2, and 3. So they're triple redundancy for the steam headers here. So again, the thermowell is mounted here with some type of flange. That thermowell goes down into the duct system here. And for this one here, it transfers that energy up, right? Changes that resistance, gives us the voltage, goes to the standardized signal, and it comes out as either 4 to 20 or a digital signal. Okay, a couple more. This one's on the bottom of a vat. So you can see here that the wiring is on the outside. Then it's got this kind of flange here. And then the RTD is mounted in the bottom of the tank to keep track of the temperature in the tank as well. So you'll see them in piping system, ducts, and in tanks as well to keep track of your temperature. Okay, you'll also see them sometimes for monitoring the temperature of bearings. So you can see that mounted just above the bearing here, they've got an RTD, and then the wiring is going out here. The transmitter isn't shown, but most likely the transmitter would be here because, again, this is just a small change in voltage or change in resistance. In order to send that off, 500 to 1,000 feet, we've got to change that value right here into a 4 to 20 or into a digital signal and send it off on our conductors. Okay, in addition to the wired transmitters, you're also going to see wireless transmitters. These ones are going to become more prevalent in industry as well. So as long as they're safe and that nobody can hack into them, then you'll see more of them. If they're able to be hacked into by hacking into the wireless system, then that'll depend on how quickly it gets used and how prevalent it becomes in industry. The same thing, it has a change in resistance that changes the voltage, changes into a 4 to 20 signal, and then is sent out as a wireless signal. In this case, it looks like it's a wireless HART protocol. Okay, that transmitter that's mounted on the top, you'll have a cut sheet for each of these guys. So you'll provide this guy with most likely a 24-volt DC power supply. You'll have a constant current that's going into the transmitter. And then depending on whether you have a 2-wire or a 3-wire. So of a 2-wire, you're going to have the conductors from the RTD going to terminals 1 and terminal 2. They call this guy a hockey puck transmitter because it literally looks like a hockey puck. So you'll have a jumper between 2 and 3 for the 2-wire, and then for the 3-wire, it'll have a terminal for each of the different terminals on your 3-wire RTD. Then, based off of the signal that's here, that'll change the signal over here. So on this current here, you'll see either 4 to 20 milliamps, or you'll see that digital output being fieldbus, Profibus, HART protocol. Okay, you can see here that this is why they call it the hockey puck transmitter. Right, they have a number of different terminals here for 2, 3, and 4-wire RTDs, and then they've got the 2 wires to provide the power source for it. They all mount in the top of your RTD thermowell here, and your thermowell is this portion right here that protects the actual RTD that's mounted on the inside. So there's the RTD mounted within the thermowell. The wires come up, connect onto the transmitter, and then you've got your 2-wire output out to the field. Okay, again, if I haven't been clear on what's going on with these guys, this is the thermowell. This is the actual RTD, and the RTD just slips right into the thermowell. The thermowell provides us with protection. There's a little bit of a drawback in that the temperature has to wick across the thermowell, then transfer to the RTD. But the beauty of the thermowell is that you can take the actual unit in and out of the system without disturbing the piping system or the ducting system. So you can replace the transmitter on the fly, and all you're doing is just taking it out of this thermowell. So you're not actually causing leaks on the piping or ducting system. Okay, just a quick little synopsis on the thermowells to finish up. Thermowell acts as a physical barrier between the process and the sensing element of the RTD. It provides protection from corrosive processes, abrasives, extremely high temperatures, and high pressure scenarios. A thermowell will also allow the RTD to be removed and serviced without interfering with the process. Things to keep in mind with respect to the thermowells would be the added cost. And because the temperature has to travel through the metal of the thermowell before contacting the RTD, the response time of the RTD sensor is going to be reduced. So obviously the main drawback of the thermowell, you're not going to get away with not using a thermowell in most cases, but things to keep in mind with respect to the thermowell would be the added cost and the fact that the temperature has to go through the thermowell, and that's going to delay your response time. All right, guys, hopefully I've covered, this is a long video. If you're still with me, you either like my voice or you're asleep and drooling on your your keyboard of your computer. Thanks very much for watching. I really appreciate you sticking with me right to the end. If I've missed anything or if I wasn't clear on anything all the way through the video, then leave it in the comments section below. If you've got photos from the field, then please send them to me so I can add them to this PowerPoint. And yeah, leave some comments below and tell me how I did with this video. Thanks very much, guys. We'll see you on the next one. Next one will be the RTD being used with the Arduino microcontroller.